Good morning or good afternoon, everyone, depending on where you are. Thank you all for being here. I'm Prof Ong. I'm from UC San Diego, and my lab is called the Materials Virtual Lab. We are a computational material science group which uses a combination of ab initio calculations as well as machine learning to design new materials. So the topic of my talk today will be on addressing errors in ab initio molecular dynamic predictions through machine learning, right? So I'm sure many of you are familiar, but just to give a very brief background of what ab initio molecular dynamics is. In ab initio molecular dynamics, you essentially are moving atoms in accordance to Newton's laws of motion, right? So if you take a look at the video on the right, essentially what you're doing is that you are moving the atoms in crystal structure. For example, let's say this very well-known lithium superionic conductor, which is Li10GeP2S12. And you move the atoms in accordance by solving the Newton's laws of motion. And in order for you to move the atoms, what you then need to basically have are the forces, right? And to get the forces, you basically solve in ab initio molecular dynamics, you actually solve the Schrödinger equation. In essence, you are solving solving DFT calculations to get the electronic structure and energies and forces, and then you are using those forces to move the atoms, right? Now, so ab initio molecular dynamics is a very powerful tool, right? So in recent years, especially as computing power has improved, many more systems are now accessible to this technique, right? Now, even so, there are certain limitations with AIMD, and though a lot of those limitations have to do with the cost of the ab initio method itself, right? So first of all, what you see here is the actual cell that we use to actually simulate this lithium superionic conductor, right? And this is just a single unit cell of this Li10GeP2S12. Is nowhere near large enough to basically get very reliable diffusion statistics. There is a chance that we might be simulating some periodic boundary effects which are spurious. And also, when we do such simulations, we tend to we usually have to run the simulations at very high temperatures, right? So typically we run that at 600K and above. Even though the lithium motion in these lithium superionic conductors are extremely fast, we still need to run them at high enough temperatures to get enough diffusion statistics such that we can then extract things like the diffusivity out of the simulation, right? And the way that you get things like the diffusivity is basically you use the Nernst-Einstein equation. You basically take the mean square displacement of the atoms with time, and then you multiply it by some prefactor, right? Now, and finally, the third limitation with ab initio molecular dynamics is basically has to do with the ab initio method itself, right? So if you are solving DFT equations to get the energy and forces, well, your simulations are only going to be as accurate as the DFT functional that is used. Now, I'm going to talk about how we are going to overcome some of these limitations today using machine learning, right? So just to give you an idea of what a typical AIMD simulation is like, just to simulate this lithium superionic conductor, we actually ran simulations for 50,000 to 100,000 time steps with a time step of 2 frames per second, and we have to run it at 4 to 6 temperatures just to be able to plot the Arrhenius plot and then be able to extrapolate down to room temperature, right? So this is an exercise that easily takes 2 to 3 weeks on a supercomputing cluster, right? Now, despite these limitations, AIMD has led to practical materials design. So as I mentioned, we simulate the the AIMD simulations at high temperatures to basically get this kind of plot where we calculate the diffusivity at different temperatures, and then we construct the classic Arrhenius plot, and then by extrapolating it down, assuming that the Arrhenius relationship holds all the way down to room temperature, we can then predict for example, what materials would have higher conductivity than others, right? So this was actually shortly after the Li10G P2S12 material was first reported by Professor Kano back in 2010. Within less than a year, we predicted that something like substituting that very, very expensive germanium with silicon or tin, you would effectively get similar conductivities or even perhaps slightly higher conductivity than the original Li10G P2S12 material. And this was in fact a prediction that was verified subsequently experimentally by Braun et al. In 2013, right? Now, however, it has also been known that AIMD sometimes fail very spectacularly, right? So I give you two examples, okay? So these are two other lithium superionic conductors. So I'm showing one work that is from my group and one work that is from another group, just so that you know that this is not an error that is made purposely, but rather is really due to the limitations of the AIMD method, right? So back in 2016, we decided to study this Li7P3S11 lithium superionic conductor. And what you see in green here is basically the AIMD simulations. And what you see in red and blue are basically, and black are essentially experimental measurements, right? And the red in and blue are measurements by the group of Professor Shirley Meng, who we were collaborating with, and black was a value from the literature. And what you notice immediately is that AIMD actually gets the conductivity of this wrong, right? We predict room temperature ionic conductivity of 57 millisiemens per centimeter, and experimentally, no one has ever been able to get anywhere close to 57 millisiemens per centimeter. All the literature reports, including our own measurements, were around 4 to 17 millisiemens per centimeter. Now, on the right, what you see is actually a more recent work from the group of Yifei Mo. Okay, so there was this lithium superionic conductor called Li3YCl6, and this was a very exciting new superionic conductor that was discovered by the Panasonic group, where they found that this conductor actually, lithium superionic conductor actually has a very wide electrochemical stability and reasonably high conductivity, right? It is not as high as, say, the sulfides, but it's still quite high nonetheless. And it is one of the first halides that has been shown to have high ionic conductivity. Now, shortly after Yifei Mo's group decided to study this using ab initio molecular dynamics, and they calculated the activation barrier, and they also calculated the room temperature ionic conductivity, and they predicted an ionic conductivity of 40 millisiemens per centimeter, right? And again, what you see here is that it is easily at least one order to almost two orders of magnitude higher than what the experiments have reported, right? Experimentally, they have only been able to get an ionic conductivity of about 0.72 millisiemens per centimeter, right? So how do we actually go beyond the limitations of AIMD, right? And to do so, we have to forego something, right? Essentially, we are going to let go of some of our strict electronic structure. So we replace this very, very expensive solution to the Schrödinger equation, and instead we replace that with some parameterization of the potential energy surface, right? In other words, what we need is basically some way to predict the energies and forces of the system with respect to the atomic positions, right? Now, this is not a new thing, right? So people have been doing this for a very long time, even before, I would say, ab initio methods, right? This is what is known as classical molecular dynamics. You basically drop the ab initio and you replace that with some classical potential. The advantage of classical molecular dynamics is basically, first of all, it's orders of magnitude faster, okay? So easily 10 to the power of 3, sometimes even 10 to the power of 7 faster, depending on what your potential is, right? the key characteristic is actually not the prefactor, but rather the linear scaling with respect to the number of atoms. What this simply means is that because we are not solving the Schrödinger equation, we are not constrained by the n to the power of 3, n to the power of 4 scaling of solving, for example, DFT solutions, right? So with classical molecular dynamics, you can easily simulate systems up to millions of atoms or even tens of millions of atoms. Now, of course, you forego something in the process. First of all, the traditional functional forms, for example, the embedded atom method that is very commonly used are too rigid. So because they are too rigid, they do not really approach the accuracy of your ab initio methods like DFT, right? So they are usually much less accurate, and this cannot be stressed enough. They are also non-transferable, right? So let's say if I'm simulating two different lithium sulfide conductors, as I've shown you the work where we studied Li10G P2S12, we did it for Li3YCl6. Other groups have done it for Li7P3S11 as well. And we can always rely on ab initio molecular dynamics in the sense that because DFT methods can be applied to any element in the periodic table, we just give it the structure and we run with it, right? Now, in order to do the same thing with classical molecular dynamics, we actually need to develop a potential for each and every one of those systems. And that is usually a much more expensive process than just letting AIMD simulations run, right? Now, that was in the past, right? But in recent years, there have been developments on this front, okay? So how do we actually parameterize the potential energy surface in a way that is reproducible and also transferable, as well as still retain close to DFT accuracies in things like predicting energies and forces, right? And this is by using machine learning, right? So this is none of this work is from my group, okay? So this has been developed by others who actually specialize in developing this what we call machine learning interatomic potentials, okay? So there are two main classes of machine learning interatomic potentials, and this is the way that I like to classify them, right? So they either describe the local environment around an atom using things like the distances and angles between the atoms, okay? So this is, for example, what are known as the Baylor symmetry functions developed by George Baylor, okay? And another class of methods essentially uses a slightly different way to describe the classical, the potential energy surface, and that's using the neighbor density. Essentially, you are looking at what is the atoms that are surrounding each atom, and you describe them using some form of some functional form, right? And after you describe them using either the Baylor symmetry functions or using symmetry functions or neighbor densities, you then convert them into some form of local environment fingerprint, right? Now, in machine learning interatomic potentials, you then use those fingerprints, local environment fingerprints, and you couple it with machine learning models, right? So either you can choose, there are a variety of them. So some of them are very simple linear models, essentially linear regression. So for example, the spectral neighbor analysis potential, or SNAP, or the moment tensor potential, they essentially just take the local environment fingerprint and express the potential energy surface as linear combinations of those fingerprints, right? There are also methods that uses things like kernel regression, for example, the Gaussian approximation potential from the group of Gabor-Sayani actually uses a Gaussian process regression method with something related to the neighbor density. And finally, you have neural networks, and George Baylor actually uses neural networks together with their with his symmetry functions. Okay. Now, so the key thing about machine learning interatomic potentials that are very different from standard traditional interatomic potentials is that because they are very well and rigorously defined, we can actually develop standardized workflows for constructing machine learning interatomic potentials for any system that we are interested in. So this is basically what my group specializes in. We basically can take a method and we can develop essentially a recipe or protocol, and we can write software to automate such calculations, right? So this was basically what we did. We collaborated with all the developers of all these interatomic potentials. We built this standardized workflow in which we essentially come up with this recipe where we generate training data from DFT for any system that we choose. So a typical approach would, for example, use ab initio molecular dynamics to run a short ab initio molecular dynamics simulation to basically generate snapshots, and then we will sample the snapshots. And then doing further DFT calculations, we can then generate a data set, right? Essentially, we have the energies and forces on one hand from DFT, and we have the structure as the input, and then we then plug it into our machine learning algorithm, and then develop our machine learning interatomic potential, right? Now, so for this particular work, we actually try to do a very expensive benchmark of different systems. So we chose things like FCC nickel, FCC copper, BCC lithium, BCC moly, and the diamond structures for silicon and germanium. And then we wanted to see basically how well do all these different flavors of machine learning interatomic potentials actually perform, right? And whether is one potential better than others, or do they generally all perform the same? So all this code is actually available open source on GitHub. So this is the link over here. If you are interested in checking them out, please go ahead, right? And the paper that this benchmarking work was published, it has been published over here, right? So the good news is that all the variants of the machine learning interatomic potentials outperform traditional EAMs by very substantial margins, right? So this is a very busy plot, but what you need to basically get from this plot is that the darker the color, the better performing it is. In other words, the lower the error in either the energies in the left and forces on the right. And what you see is that all the machine learning interatomic potentials almost always outperform the EAM and mean potentials for the same system, right? That are available in the literature. So, and this is consistent throughout all the 6 systems that we studied, right? The other thing is also that if you, depending on the choice of the machine learning model, it actually affects the amount of training data that you need to basically train the machine learning interatomic potential, right? So this is basically a convergence plot which shows for each of the different machine learning models, machine learning interatomic potentials, what's the error, the test error in the energies and forces with respect to the number of training structures. Now, of course, certain methods, for example, like the neural network potentials, because neural networks are notoriously data hungry, you actually require a lot more training structures for convergence to occur, right? However, the good news is that for most of the methods, you actually do not need that much training data, right? So we find that essentially by the time you hit about 300 something or 400 training structures, you can essentially get a very good machine learning interatomic potential. And that's good news, right? So essentially what this means is that as long as you're doing the sampling of your AIMD right, and you are covering a good enough diversity of local environments in your sampling, you can already get very good machine learning interatomic potentials in terms of energy and force errors, right? And this is something that I would say is quite revolutionary, right? So if you ask us 10 years ago, let's say, can we always get a good EAM for this particular complicated system? The answer would be, well, maybe, but maybe not, right? So there's a lot of uncertainty there whether we can get something that's good enough. Here we are essentially showing that just with a certain fixed recipe, you can actually get most of it correct, right? We also evaluated things like the cost and complexity. The main thing to note here is that things like the moment tensor potential, neural network potential, and the snap potentials all have a very good trade-off between cost and accuracy. The gap potential, because of the use of the Gaussian process regression, they tend to be much more expensive, but at the same time, they can reach the best accuracy among all the interatomic potentials. So depending on what you need for your simulation, this is something that you can tune to your liking, right? So this has really enabled us to do certain science at certain scales that we would not be able to do before. So for example, this is we actually developed a machine learning potential for the nickel moly system, and we studied things like, well, can we reproduce the high temperature phase diagram of nickel moly, right? And here you can see how the machine learning interatomic potential essentially captures chemistry in a way that traditional EAMs may fail, right? So if you look at this moly-rich region of the phase diagram, you'll see that the EAM actually predicts that nickel has a very high solubility in molybdenum, right? And traditional things like CalFET, which is essentially based on experiments, actually show that you actually have very very low solubility of nickel, right? And what you see on the blue line here is that the machine learning interatomic potential, here we actually use the snap potential formalism. You basically get almost the correct solubility of nickel in moly. We also get the melting point of molybdenum much closer than your EAM potential. Now, once we actually get a good potential, we can then do very, very interesting things, right? So we can, for example, construct these polycrystalline models of our alloy. So this is actually a nickel moly alloy with grains that are between 4 to 11 nanometers, and this basically is a simulation cell of 1 million, on the order of 1 million atoms. We can basically study what's the stress-strain relationships. You can reproduce, for example, the Hall patch strengthening effect, as well as the inverse Hall patch regime below 10 nanometers in our simulations, right? More recently, we have actually gone beyond just two component systems. We have gone to things like high entropy alloy systems, where we basically have four different elements in equiatomic, nearly equiatomic proportions, and we can then we develop an interatomic potential for this four component system, and then we studied, for example, what is the short range order in the high entropy alloy, as well as what's the effect of things like segregation on the high entropy alloy, right? So for example, one of the key findings that we have in this work is that high entropy alloys is really somewhat of a misnomer, right? The high entropy comes from the assumption that you essentially have almost a perfect solid solution in the alloy. What we found was that was not the case, right? So first of all, when you actually have a polycrystalline system, we found that niobium tends to segregate to the grain boundaries of this polycrystalline system. And not only that, within the grains themselves, you actually find increased short range order. In other words, you have elements that like to sit closer to each other and elements that like to stay further away from each other. And that actually has a significant effect on the things like the mechanical properties of the alloy, right? Especially the polycrystalline alloy. So, for example, if you look at the random solid solution alloy, we find that there's a lot of strain on the grain boundaries when you do a stress strain experiment, while when you actually do it on the one with the equilibrated system with this niobium segregation, you have significantly reduced strain, right? So this is actually a key finding, right? That you would not have been able to do via either ab initio molecular dynamics or any simulations using your traditional EM potentials. Okay, so but the topic that I want to focus for the last part of my talk is really on the topic that I talked about earlier, right? Which is how do we use machine learning interatomic potentials to study things like lithium superionic conductors, where we have done extensive AIMD simulations, and many of those AIMD simulations seems to be giving us, well, at least some of the simulations seems to be giving us wrong predictions, right? So what we have done is that we basically selected 3 different chemistries of lithium superionic conductors, Li3YCl6, Li7P3S11, and this lithium lanthanum titanate, right? All these are complex multi-component ceramics, okay? So they all have at least 3 to 4 components, all right? And thank you, Natalie. Yep. We also purposely chose it such that there are 3 different anion chemistries involved, and the room temperature ion conductivities range from 0.1 to about 10 millisiemens per centimeter for all these systems, right? We then developed this workflow to basically construct machine learning interatomic potentials for all 3 lithium superionic conductors. Here we actually use the moment tensor potential formalism, okay? So the way that we do this is basically we start with a DFT relaxation, we then do AIMD simulations at different temperatures and at different strains. We then collect snapshots from our AIMD simulations, and then we do static DFT calculations to calculate the energies and forces. And finally, we then do our machine learning MTP fitting and validation, right? Now, a key question that we wanted to explore in this work was to basically, what DFT functional should I use for all these simulations, right? This training data generation, right? So for most of the work, if you look at the literature, they all use PBE, right? PBE is sort of like our go-to functional for everything, right? Now, but we want to see, well, is PBE giving us the wrong result sometimes, right? So we look at both PBE and OPT-B88, which is this van der Waals functional, and we look at whether, well, does it matter whether we use PBE or OPT-B88 to generate the training structures versus calculating the actual energies and forces that are going to go into our machine learning model, right? And in doing so, we actually generated a suite of 3 different MTPs for each superionic conductor. PBE just means that I use PBE for both the training structure generation as well as the energy calculation, while PBE OPT-B88 means that I'm using PBE for the training structure generation and OPT-B88 for the energy and force evaluations, right? Now, this is just a standard parity plot to show you that, we have gotten down our machine learning interatomic potential fitting to basically a very good level. We can get low energy and force errors. I just show you one of the plots just to convince you that that's the case, and it applies to all the different temperatures that we did our AIMD simulation in, okay? So we first look at, for example, things like the errors in densities that are predicted by our PBE and OPT-B88 versus the one that is predicted by our moment tensor potential constructed using PBE or OPT-B88. Now, one thing you immediately notice is that at least for the Li3YCl6 and Li7P3S11, it matters significantly, right? OPT-B88 definitely gives you lattice parameters and densities that are much closer to experiments compared to PBE, right? And the other thing that to take note from this graph is that our moment tensor potentials that are built according to this the training data from these calculations, they essentially reproduce the errors. And this is not surprising, right? You have garbage in, you have garbage out, right? So I'm expecting that if I build a potential using PBE, that potential is going to reproduce the errors of PBE. And that is essentially what we are seeing here, right? So, and for example, this is the MTP PBE, and this is the actual PBE calculations, and you see that the errors are relatively similar. And conversely, if you use OPT-B88, the OPTP88 error is reproduced, right? So we also look at things like the EOS curve and equation of states, and again, the message is still the same. Essentially, you reproduce the EOS curve of the corresponding DFT functional that your MTP is based on. Now, this actually has critical implications for machine learning interatomic potential development, right? Because classically, people have always tried to build the potential using the same functional. And what we show here is that essentially you can decouple the choice. You can use PBE for structure generation and use OPTP88 or some other more accurate functional to calculate the energies and forces, and you can still get a very good functional, good potential, right? Now, basically the machine learning interatomic potentials then enable us to study things like long time scale, nanosecond version of our MPT-MD simulations, and we can then construct these very, very nice Arrhenius curves. And what we essentially found was that our predicted ionic conductivities are now much closer to experiments. And the reason why this is the case is that there is this transition occurring at 400 to 525 K in almost all the lithium superionic conductors, right? And because of this transition between two different linear Arrhenius regimes, the actual room temperature ionic conductivity is actually significantly lower than what you would have gotten if you just extrapolated down, for example, your AIMD simulations at high temperature, right? And you can see that the agreement here is extraordinary, right? In fact, it is somewhat a little bit too good to be true. It is better than I would say even that what I expected. And these transitions at low temperatures is not something new again. So this is something that has been observed in experiments in a few systems. For example, LLTO. Sockers et al. Has already reported something like this back in 2011, and our transition temperature are also in very good agreement with what they observe, right? So what remains really to see is that if experimentalists can reproduce the observed transitions in the Li3YCl6 and Li7P3S11 that we simulated. Now, so we also look, because we are able to do the simulations, we can look at what are the origins of this non-Arrhenius transition. And basically what we found was that in all three cases, what is happening at the transition is that you have activation of new diffusion pathways and also a change in the diffusion dimensionality, right? So as you go across the transition, you essentially activate different diffusion pathways, and you change, for example, the dimensionality of diffusion from either 1D or 2D to a 3D diffusion. And that is the reason for the lower activation barrier at the higher temperature regime, right? Okay, so just to conclude, ML-IAPs provide an automatable approach to basically bridge this length and time scale gap that we have between empirical potentials and first principle methods. They do reproduce the errors of the DFT functional. So, but the good news is that generating the structure snapshots, you can essentially use whatever is the cheapest functional that you can get away with, or even a non-DFT method. But you do need a good functional to get correct energies and forces. And finally, even with those limitations, given with extended time and length scales that are accessible via ML-IAPs, we can actually get surprising new insights into lithium superionic conductors. So just want to acknowledge funding from Samsung and Nissan, and this is the members of my group, and especially my postdoc Chichen, Yunxing, my graduate student who just graduated, and Qi, who was the first author of this work. And I'm happy to take any questions. Thank you. Mm-hmm. Yep. Natalie, perhaps the easiest way is that I will read out the questions and then I will answer them, and then at least those that are fully formed. So for Maria's question, okay, so the question was couldn't the discrepancy in ionic conductivities between experiments and predictions be due to grain boundaries? The answer is maybe, but in most of these cases, the grain boundary, the conductivity is measured experimentally. They try to measure both the bulk and grain boundary conductivity. So what we are looking at essentially is the reported bulk conductivity, um, and in these cases, it is not due to the grain boundary effect. At least we don't believe that it is due to the grain boundary effect. Okay. All right. And then the next question is by Professor Kieran Burke. He said he has a question about training structures, but he didn't elaborate. Kieran, do you want to ask? Okay, maybe I'll move on to the next question first. Oh, yeah, someone raised the hand. So, oh, no, okay, so that's another question. So, Andre asked a question about, I'll be curious to hear your thoughts about the possibility of treating excited state forces with such a framework. Well, I would say that it's possible if you can get the DFT data for the excited state. If you get accurate enough data, I think that shouldn't be a problem. So at least I'm optimistic that it can be done, right? Okay. So in other words, I would say that anything that your electronic structure method you can do via first principles, you should be able to do it via machine learning interatomic potentials, as long as you do not go too far out of bounds, right? So I would say that the main things that you can't do is things like, for example, if there's a lot of electron transfer occurring and you are trying to simulate reactions happening, right? So now that clearly is something that, given that your machine learning interatomic potential doesn't treat electrons, you're not going to be basically have a lot of luck doing that, right? So I think that's basically um, the answer. Okay. Okay. Yeah. Kira. Mm-hmm. Mm-hmm. Yeah, thank you for that question. Yeah, indeed. I think when we were doing this work, we were doing it in a very naive way. Essentially, we sample every 10, 20 picoseconds, and then we just, hopefully, we sample a good enough diversity of structures. We did do things like, for example, use a PCA analysis of the local environment descriptors to basically try to figure out whether we are essentially always sampling the same space or not the same space. Now, recently there have been additional developments where essentially what you're doing is that you're doing some form of active learning to basically select the structures that you are going to incorporate back into the training structure to further improve the training, the accuracy. And we have experimented with that, and those work phenomenally well. So now the convergence of the machine learning interval potential is actually much faster. We can do that with even fewer structures, and we can also get a good sense of how far our machine learning interval potential can be extrapolated. So people like Alex Shapif have actually done a lot of work in this area for his MTP potential, and that's what we have been using. So